This lesson will cover how to graph a quadratic equation when it's in standard form. There's several things that we need to cover before we attempt to graph a quadratic. It helps to first start with taking a look at what shape we'll get when we graph. Each type of function has a specific shape when you graph it. In the case of a quadratic equation, you end up with something called a parabola. You end up with a parabola. Now there's several key features of a parabola that we need to talk about. Here's an example of a parabola down here. A couple of the key pieces of information about the parabola that we need to note is number one, the x-intercepts. The x-intercepts are the locations where the graph crosses the x-axis. In our case, you can see that the x-intercepts are labeled right here, and the two locations here and here are where our parabola crosses the x-axis. Now it is important to know that there are either 0, 1, or 2 x-intercepts. Sometimes there's 2. You can imagine if the parabola was up higher, you see that there's a turnaround point on the parabola. If the parabola was up higher, it potentially could never touch the x-axis. Or if this turnaround point, which is labeled the vertex, which we'll talk about in a second, comes down and just touches the x-axis, it's only touching the x-axis in one location. So you either have 0, 1, or 2 x-axes. The next thing to mention really quick is the y-intercept, sometimes also referred to as the initial value. This is the location where the graph crosses the y-axis. Now, for us, in the example parabola we have down here, that location, the y-intercept right here, is down at y equals -3. Another side note on the y-intercept is that you will always, with a parabola, always have one and only one y-intercept. The next piece of information that's important to discuss is what's called the vertex. The vertex is the maximum or minimum value of the function. This can also be thought of as the turnaround point. If we look at our example here, you can see that our vertex is down here right at the minimum value of our parabola. Okay, the minimum value of our parabola. It's also the point at which our graph turns from decreasing in value as we look from left and right to increasing in value as we look left to right. So that's why it can be called the turnaround point as well. But technically it's viewed as either the maximum or minimum value of the function. Okay. Lastly, as a piece of information here, you have the axis of symmetry. This is the vertical line that intersects the vertex and splits the graph into two halves that mirror each other. So right here we have our line of symmetry is this line right here, highlighted again in blue. We've got this line right here as our axis of symmetry. Again, this line, as you can see, goes through the vertex and splits our graph in half, and each side is a mirror image of the other side. It's also important to label the line of symmetry. The line of symmetry is a vertical line. A vertical line, the equation of a vertical line, looks like x equals, and then whatever value this line crosses the x-axis. In this case, it's at 1. So x equals 1 would be the equation of this line of symmetry. It's going to be important for us to label that when we get to graphing these quadratic equations. Now, something to note real briefly over here, again, we're working with quadratic functions in standard form. Okay. The example that we've looked at, just to illustrate the major key components of a quadratic, the parabola opens up, meaning the open side is up and our vertex is at the very bottom. It's a minimum value. You can see over here though, we have two separate examples. One that looks very similar to that, in which the minimum, or in which the parabola opens up, and like the example we looked at, our vertex right here, vertex point right there, is a minimum. Now we know that this is going to be a minimum if, as we can see right here, the value of a from our quadratic function, the ax squared plus bx plus c, if the value of a is greater than 0. So if the value of a is greater than 0, our parabola will open up, like this example, and the vertex will be a minimum. However, if the value of a is less than 0, in other words, negative, we have this situation over here at which we can see our vertex is no longer the minimum point. Our vertex is the maximum point on our parabola. And again, the parabola opens down. The parabola opens down. So those are the key features of a parabola, the shape that we get when we graph a quadratic. Now, in order to graph a quadratic, everything starts with the vertex. The vertex is the key piece of information that we need to find in order to graph a quadratic to get the parabola. So right here, what we have is we have the vertex formula. It's a formula that if given y equals ax squared plus bx plus c, we can find the coordinates of our vertex. It's important to remember that the vertex is a coordinate on a coordinate plane, meaning it has both an x and y coordinate. The x coordinate is calculated as negative b over 2a. That negative b and the b and the a come from the y equals ax squared plus bx plus c. Okay. Once you have the x-coordinate, to find the y-coordinate of your vertex, you simply plug your x-coordinate into your function and solve for y, and that gives you the y-coordinate. So to find the x-coordinate, it's negative b over 2a. To find the y-coordinate, you plug whatever you got for your x-coordinate back into your function and solve for y to get your y-coordinate. In a single formula, it looks like this. The coordinate point xy, which is your vertex in this case, is the coordinate point negative b over 2a. There's the x-coordinate, and f of negative b over 2a. In other words, you're taking the x-coordinate, negative b over 2a, and plugging it into your function f to find your y-coordinate. Okay, we'll end up using that formula in the examples that we have next. Just as a real quick step-by-step process, here's the process we're going to follow as we graph the two quadratics that we're going to look at. Number one, you want to calculate the coordinates of the vertex and plot this point on the coordinate plane. The next step is the key step. We're going to end up constructing a t-table around the vertex. This means to select x values for the t-table on both sides of the x-coordinate of the vertex. What we're going to find is we'll pick at least 2 points on either side. Number three, we're going to evaluate each x value selected in your t-table for its corresponding y values. What's nice about that is then we will be able to do step 4, which is to plot the coordinates calculated in your t-table on the coordinate plane. From there, it's as simple as step number 5, connecting the points on the coordinate plane that will be in the shape of a parabola. And lastly, as a form of accounting for everything, we're going to label the vertex and 2 additional points, as well as draw and label the axis of symmetry. Let's now look at our very first example. Very first example that we're going to graph is y equals x squared plus 6x plus 5. So if we recall the steps that we just went over, the very first step is to find your vertex. So we need to find our vertex first. If you recall, to find your x-coordinate of your vertex, it was simply negative b over 2a. So for us, that equals negative b value here from our quadratic is 6. So that's going to be a negative 6 divided by 2 times a. A in this case is 1. So this gives us negative 6 over 2, which finally gives us a value of negative 3. So the x-coordinate of our vertex is negative 3. Now you recall, hopefully, from how to calculate the vertex that in order to calculate the y value of the vertex, it's as simple as taking what you just found to be your x coordinate of your vertex and plugging that in to your equation. So it's going to end up being that the y coordinate is equal to negative 3 squared plus 6 times negative 3 plus 5. So simplifying this gives us y equals negative 3 squared, which is 9, plus 6 times negative 3, that gives us a minus 18, and then plus 5. Finishing this off, 9 minus 18 is negative 9. You add 5 to that, and you end up with negative 4. And there is the y-coordinate of our vertex. So we found that our vertex is the point negative 3, negative 4. So I'm going to go ahead and find that point on my graph. Negative 3, negative 4. Go over to negative 3 and down to negative 4. That's this point right here. Negative 3, negative 4. So that's the point that is my vertex. That's the point, that's the vertex of my parabola. Now, if we recall, we can tell whether the parabola opens up or down by the value of a. The value of a here, the coefficient in front of x squared, is 1. That's a positive number. That means the parabola should open up. The parabola should open up. Okay? It's just something to keep in mind to make sure that as we progress, we're getting answers that make sense. Because the next step that we want to do is we want to create a t-table around our vertex. So here's what this looks like. Here is my xy t-table. And we found that our vertex was negative 3, negative 4. Negative 3, negative 4. Now I'm going to pick x values on either side of my vertex. So keeping it simple, nice numbers to work with, I'm going to keep it as negative 2 and negative 1 and negative 4 and negative 5, 2 numbers on each side of my vertex. What this will do is it'll give us a few points on either side of the vertex to give us that shape of the parabola that we're looking for. Now that we've selected these values, we need to take them and plug them in back into our equation y equals x squared plus 6x plus 5. The way I like to do this is I like to kind of segment this off really quick, and over in this region over here, do the work to get what I'm looking for. So what I'm going to do is I'm going to plug in negative 1 to my function. That gives me negative 1 squared, which is 1, plus 6 times negative 1, which gives me negative 6, and then plus 5. So plugging negative 1 right here into each of the x's in my equation up here gives me 1 minus 6 plus 5. 1 minus 6 is negative 5, and you add 5 to that, and I end up with this equaling 0. So when I plug negative 1 in, I get a 0 for my y. Let's do the same now with our negative 2. If I plug negative 2 into my function above, up here, what do I end up with? Negative 2 squared is positive 4. Then if I add 6 times negative 2, that actually gives me a minus 12 with a plus 5. And what does that equal? 4 minus 12 is negative 8, plus 5 gives us negative 3. So I know that when I plug negative 2 in, I end up with a negative 3 for my y value. Now from this point, finding the y values for the negative 4 and the negative 5 are actually fairly straightforward because of how we know a parabola behaves. We know that around the vertex, a parabola is symmetric, which means that if my x values are evenly distributed on each side of my vertex, that whatever I get for negative 2, I should also get for negative 4 because it is the same distance from the vertex, just on the opposite side. And because a parabola is a mirror image of itself across the vertex, across that line of symmetry, I know that if I plug in negative 4, I'm going to get negative 3. And likewise, because negative 1 and negative 5 are each 2 units away from the vertex on either side, I know that if I plug in negative 5, I'm going to get the same y value as when I plug in negative 1. So if I plug in negative 5, I'm going to get 0. Saves me some time in having to evaluate negative 4 and negative 5. That's one reason why I chose the x values I did, so that the x values were mirror images around our vertex of negative 3, negative 4. Now that I've got my t-table, the next step is simply to plot these points. So I'm going to go ahead and plot these points. So negative 1, 0 is this point right here. We've got negative 2, negative 3, which is this point here. We already have our vertex of negative 3, negative 4. The next point is negative 4, negative 3, which is a nice mirror image of the point on the other side of the vertex. And lastly, we have negative 5, 0, which again is a nice mirror image of the other point on the other side of the on the other side of the vertex. If you look at these points, hopefully you can see that they line up very nicely in the shape that we expect, a parabola. So connecting these dots ends up giving us something that looks like this. And there we have a parabola, which is the graph of the function up here, y equals x squared plus 6x plus 5. Now again, as a way of accounting, we want to label our vertex right here, which is negative 3, negative 4. We want to label 2 other points. I'll label this point right here at negative 2, negative 3. And I'll label this point right here, which is at negative 1, 0. Negative 1, 0. And last but not least, we want to also label our axis of symmetry. Our axis of symmetry is again that line that intersects the vertex. So our axis of symmetry will be this line right here. A vertical line that goes through the vertex, and the coordinates, or rather the equation of that line, because it's a vertical line and goes through the point negative 3, this line has the equation x equals negative 3. Here we have our parabola, vertex, 2 other points properly labeled, axis of symmetry drawn and also labeled. To solidify some of these concepts in graphing a quadratic, let's go ahead and do another example. So here's our next example. We have the equation y equals negative x squared plus 6x minus 3. Again, the very first step is to find the vertex. So to find the vertex, we know that the x-coordinate of our vertex is simply negative b over 2a. Well, my b value is 6, and my a value in this case is negative 1. The 1's not there, but the negative is, so we have to do negative 1. So negative b over 2a, b is 6, so negative 6 divided by 2 times a being negative 1. So negative 6 divided by negative 2 is what that becomes, and gives us a final answer of the x-coordinate of our vertex being 3. So now we have the x-coordinate of our vertex here, which is 3. So we can start working with that now. Well, we can use the x-coordinate of our vertex to now find the y-coordinate of our vertex. Again, hopefully we remember that to find the y-coordinate of our vertex, we simply take what we got for the x-coordinate, which in this case was 3, and plug that into our function. Now we've got to be careful here because the 3 goes in for the x value. So at the very beginning we have negative, and then I'm going to write it as 3 squared because the negative is not getting squared, only the 3, plus 6 times 3 minus 13. This produces for us that the y is equal to negative 9 plus 18 minus 13. Well, negative 9 plus 18 is positive 9. Subtracting 13 gives us negative 4. Gives us negative 4. So now that we have our vertex of 3, negative 4, we want to go ahead and plot that point on our coordinate plane. So the point 3, negative 4 is over at 1, 2, 3, negative 1, 2, 3, and 4. 3, negative 4 is this point right here. So we've got that labeled, and just like the example we did before, the next step after finding our vertex is to build a t-table around our vertex. So here's our xy t-table, and in the middle we're going to put the point 3, negative 4. And again, we want to pick 2 values on either side, 2 values minimum, on either side of our vertex x value. So I'm going to pick 2 and 1, and 4 and 5, again keeping it nice and symmetric so that I can calculate just half of them and then mirror the y values over to the other x values as we did in the previous example. So let's start here with negative 1. Plugging negative 1 into our function above. 1 squared is 1, then there's that negative on it, so negative 1. 6 times 1 is 6, so negative 1 plus 6, and then minus 13. What does that produce? Negative 1 plus 6 is 5. And then if you subtract 13 from that, it produces negative 8. So when we plug in 1, we get a y value of negative 8. Next, let's plug in our value of 2. So plugging in 2 for x, we end up with 2 squared, which is 4, but then we have that negative on it, so negative 4. 6 times 2 is 12, so that's negative 4 plus 12, and then the minus 13 at the end. And what does that equal? Well, negative 4 plus 12 is positive 8. When I subtract 13 from that, I end up getting a negative 5. So when I plug 2 into my function, I'm ending up with a y value of negative 5. Now again, this is nice. We're going to save half the work because since the value of 2 is the same distance from the vertex as 4, just on the different side, because parabolas are symmetrical, we know that if we were to plug in 4, the y value we would get out is negative 5. And likewise, because 1 and 5 are both the same distance from my vertex, the x-coordinate of my vertex. They're both 2 units away on either side. I know that since I got -8 for my value of 1, x value of 1, I know that I'm going to get -8 for an x value of 5. So with our t-table completed, we can now plot these points. So 1, -8. 1, -8 is this point right here. We have 2, -5, which is right here. We've got 3, -4, which is our vertex already plotted. We have 4, -5, which is this point here. And lastly, we have 5, -8, which is this point here. Again, nicely lines up in the shape of a parabola for us to connect. And as we connect these dots to get our parabola, what we'll notice is that it opens down instead of up. It's a little different than the previous example, but it is what we expected. Our value of a up here in our equation y equals -1x squared plus 6x minus 13. The value of a is -1, less than 0 from the chart we saw on the first page. If our a value is less than 0, our parabola opens down. Now there's a couple housekeeping things we need to do with this parabola. Number 1, label the vertex. Labeling our vertex here, that's 3, -4. We also need to label 2 other points. I'll go ahead and label this point, that's 4, -5. And I'll label one on the other side over here. I'll label this point over here, which is 2, -5. Okay, and last but not least, we need to label our vertex. Not our vertex, sorry, our axis of symmetry. So to do that, we know that the axis of symmetry is a vertical line. Oh, let me undo that real quick. It's a vertical line that goes through our vertex, right there, and splits our parabola in half so that each side is a mirror image of each other. The last thing to do is label label the axis of symmetry. And we know that the equation of a vertical line is x equals, and then wherever it crosses the x-axis. In this case, it's at 3. So x equals 3 is the equation of our axis of symmetry.